Great, so let's kick off the finite element method and let's start talking about how we're going to represent information. And this video is just quickly to give you an overview of why at all, okay, why we would go this route at all. So first off, what I would like to do is just let's imagine almost solving the problem that we did last week, but let's imagine we trying to solve it with two fields. Okay, so two fields, because this is by far the easiest way to understand the finite element method, the decisions that I made. So if I say my one field is u1 as a function of x, ax squared plus bx plus c, and let's say this is x, let's say this distance is 2 meters, and then let's say we've got another field this side, u2 as a function of x is equal to dx squared plus ex plus f, and let's say this distance here, if I go on there, or let's say this coordinate here is then, that's bad. Let's call it this distance to be quite confusing. It's another 2 meters, so this is 4 meters. But that doesn't matter so much, it's just to put things into context. So if I wanted to do this, then I had to make sure, for instance, that at this point, that the displacement is such that there's not a gap forming or things overlapping. I can't have the structure moving into itself or all of a sudden have these two things come apart. So what I need to make sure of is the whole time I need to enforce that u1 at 2 meters is equal to u2, this field, at 2 meters. And every time I have these places where two fields need to meet, I need to build in these kinds of conditions. I need to build in constraints to make sure that that's okay. So I have here essentially 1, 2, 3 unknowns, and I've got here 1, 2, 3 unknowns. Okay, and as a big motivator for why things will look the way they look in the finite element method is the fact that if you carefully think about what's going on here, when you put in this equality constraint by saying u1 is at 2 meters must be equal to u2 at 2 meters, we are essentially saying, you know what, there's not really 3 unknowns here and 3 unknowns here. Maybe in this side, or let me put it like this, maybe between these two problems, there's actually an unknown extra, too much. And the way we get rid of that and say if there's an unknown too much is we put an equality constraint in to reduce essentially one of the freedoms. Okay, so this is really what's going on here, is by saying we constructed a displacement field with 3 variables and a displacement field with 3 variables, but we need to make sure we actually reduce the freedom of this field and of this field, because they need to be such that at u1 2 meters and u2 2 meters, that they're equal to each other. And so that's what the finite element method will try and do, is to say, why can't we just construct it such that we don't have to do these enforcements the whole time, because this is going to be tedious. If every time, especially you can imagine if this becomes in 2D and 3D, if for instance you had in 2 dimensions you had a field like this with, let's say, a displacement field that I've got over this, and now I've got another displacement field patch here, and now I need to make sure that things don't go into each other and stuff like that on those edges. Can you imagine the chaos with enforcing a constraint on a line like that? So that is essentially, this is not going to work well if you generalize this approach. But what the finite method said is, well, let's look at the same problem. Okay, let's look at the same problem, and let's introduce essentially the freedoms that we have. Okay, but look here. So here was 1, 2, 3, 4, 5, 6 variables here. 6 variables, 1 equality constraint. Which really, what an equality constraint does is it actually says, you know what, we can solve for one of these variables, one of these things. So there's actually, if we enforce this, you can think of this problem as only have actually 5 variables. Okay? And now I want you to see the analogies and the parallels with what's below. How many dots did I put down? 1, 2, 3, 4, 5. And let's say we construct, we have an approach to be able to say Q1, Q2, Q3, Q4, Q5. That these Q1, 2, 3, 4, and 5 are like these A, B's, and C's, but such that Q1 represents the displacement at this node, Q2 represents the displacement at this node, Q3 represents the displacement of this node, Q4 represents the displacement of this node, and Q5 represents the displacement of that node. Is that they are the variables that we want to solve for, like the A, B's, and C's, but they have a bit of a different meaning. That they actually also physically mean that this node's displacement is just given by Q1. This node's displacement is just given by Q2, Q3. And the beauty is all of a sudden, now I'm asking you the question, is it possible for a gap to form here? Is it possible that these things go into each other or that they pull apart? Well, the fact of the matter is if I solve this problem, yeah, and I think about solving this problem, we share this node here. And so it's, by construction, it's physically impossible. Why? Because Q3 here, this side here, for instance, this Q3 here, means it's the displacement of this node. Okay. And the equivalent would have been, if I were to show you, if I want to go back to something here with an equality constraint, is if I were to say what we solved was the following. So to make sure that you understand the analogy of this problem, where we have now essentially the same number of variables, where it's going to go back to 6. So this is the finite element way of doing things. This is just the this is maybe just to relate this back to this. So you can see that I'm going to go back to 6 variables by saying, let's say Q1, Q2, Q3, Q4, Q5, and Q6, for instance. Okay. If I wanted to go, if I wasn't thinking clearly, I might have constructed something like this and said, okay, so this is what I want to do. Still, I would like to have the meaning that Q1 means the displacement of this, Q2 the displacement of this, Q3 the displacement of this, Q4 the displacement of this, 5 and 6. But that I use Q1 to Q3 here and I use Q4 to Q5 here. Okay. If I wasn't thinking clearly, I would have then every time I just say, okay, Q3 is also then equal to Q4. Yeah. So that I can solve. So I can solve for Q1, Q3, 4, 5, 6. In addition, then enforcing this, and what the finite method is saying, you know, this is just crazy redundant. We don't want to have sort of duplicate nodes at the same spatial location. We just want to say, you know what, make this one thing, and then we go back to this problem here. So just make this a single node Q3. Doesn't matter, and then we can renumber these maybe as Q4 and Q5. So this is just to make sure that you understand what the decisions are of the finite method, why they are so important, and what we buy with them, that we avoid these kinds of things all the time. Okay, so that is hopefully just a quick introduction and a motivation for why things will look the way they look. So let's look at the next video. How do we construct then, sort of even over this, such that a field that is quadratic over this, but such that it only has the value of Q1 here, the unknown Q2 here, and the unknown that we will solve for Q3 at that node there. Okay.